section 5.4 is application of what we know from what we've learned from exponential functions and logarithmic functions, right? So in this section we do what is called exponential models. And our models are of the form a of t is equal to a sub 0 times e raised to the kt power. Okay? So k times t is the exponent on the number e. And this quantity, e to the kt power, is being multiplied by a real number, a sub 0. So a of t stands for the amount of a population or substance at time t. Okay? So we can sort of explain it up here. Right? The exponential growth model is used to model the quantity of a substance or population that grows with time. So the independent variable in this case is t for time, not x. Okay? And time normally starts in our models at 0, right? Technically, most of the time we don't allow for negative time. So t, right? So the domain is t greater than or equal to 0. Okay? And a of t, which I just pointed out, is the amount of a substance or size of a population at time t, right? Starting at t equals 0. A sub 0, you put 0 in for t, and you get a sub 0, or a of 0, is equal to a sub 0, and that a sub 0 is called the initial amount, or the initial population. That's what you're starting with. K in our model is called the growth constant, or growth rate, and it determines how fast the population, or the amount of the substance, increases over time. It can be shown that the time for a substance or population to double in size is equal to the natural log of 2, that's a real number on the real number line, divided by the growth rate k. And given the time it takes for a population to double, or a substance to double, you can calculate the growth rate k by dividing the natural log of 2 by the time it takes for a population or substance to double in size. Okay. So the graph of our exponential model looks like this. So instead of an x-axis, right, we have a t-axis. And the vertical axis, right, is y equals a of t. Remember, y values and function values are the same. And here's t equals 0, right, on the t-axis, right? So time starts at 0. And we just said at a of 0, okay, the function equals a sub 0. So that's the y-intercept, okay? So at t equals 0, the amount of the population or substance is a sub 0. And then it grows exponentially from that point on. And you know the graph of the exponential function, right, looks like that. So this gives us, this is the graph of the amount of a substance or a population as time increases, okay, as t increases. Okay. The population or the amount of substance increases exponentially. Okay. So in the first exercise, we're given initially 300 bacteria in a culture are present. So it says the initial 300 bacteria in a culture are present. So that means a sub 0 is equal to 300, right? That's the initial population. After 9 years, it observed that the number of bacteria has doubled. Well, we started with 300. It doubled in 9 years, so it went from 300 to 600. So the amount of bacteria 9 years later, a of 9, is equal to 600, right? So the number of bacteria has doubled. So the time it takes for the population to double is 9 years. So capital T is equal to 9 years. Okay. So I'm just filling in information in this rectangle that I know from the problem. Okay. Part A asks, find an exponential model for the number of bacteria in a culture after T years. So we got to find the model, A of T, for this problem down here, this exercise. Okay. Well, we're given the time it takes to double. So the growth rate K in our model, remember T is the variable, is the input variable. Okay. K is a real number, A sub 0 is a real number. So the growth rate is equal to the natural log of 2 divided by the time it takes for the population to double. So K in this case is equal to the natural log of 2, right, which is a real number, divided by T. Big T, well, big T is equal to 9 years. So the exact value, so there are no calculators, right, on the exams. So you got to give exact values, right, no decimal values. So the growth rate, the exact growth rate is the natural log of 2 divided by 9 in this problem. Okay. And now we can substitute for A sub 0 and K to get the exponential model for this problem. Yes, ma'am.
Would A of 0 also equal 300?
Yeah, A sub 0 is equal to 300, right? That we observed that. Okay, yeah. So A sub 0 is equal to 300, and K, the growth rate, is equal to natural log of 2 over 9. And now we just substitute for A sub 0 and K to get our exponential model. Okay. So we have A of T is equal to A sub 0 is 300. K is the natural log of 2 over 9. So you gotta be really careful how you write this, because this is an exponent, right? K times T is an exponent of the number E. And so we have the natural log of 2 over 9 times T. This natural log of 2 over 9 times T is an exponent on the number E, right? You don't write it at the same level as E, you write it as an exponent. Okay. So this is our exponential model that tells us how many bacteria are in a culture at time T. The T is in years, right? And remember, T is greater than or equal to 0, right? Can't be negative. So if T is equal to 5, this model tells us how many bacteria there are in a culture 5 years. 5 years from now. Yes, ma'am.
So when you're asked to find the exponential model, you only fill in A of 0 and K.
Right, because E is a number and T is a variable. Yep. All right. In B, it asks, how long will it take for the bacteria culture to grow to 1,000 bacteria? Okay. So this is the answer to A. How long will it take for the bacteria culture to grow to 1,000 bacteria? How long? Well, this is a time question, right? How long in years will it take for the bacteria culture to grow to 1,000 bacteria? Well, so we're solving for T in this problem, right? T is the unknown, the amount of time it takes for the bacteria to grow to 1,000 bacteria. So, to answer that question, remember A of T tells us the amount of bacteria at time T, right? So A of T in this case is equal to 1,000. Right? Some future point, there will be 1,000 bacteria in our culture. And we have to figure out at what point in time, right? How far down the road will it be until we have 1,000 bacteria in our culture? So we replace AFT on the left here with 1,000 and solve for T. Okay. We know how to do that, right? We're math geeks. We know how to solve for T, right? So we have 1,000 is equal to 300 times E raised to the natural log of 2 over 9 times T power. Now solve for T. Okay. Well, this is a product on the right hand side, so we can divide both sides by 300, right? And when we do that, we have 1,000 divided by 300 simplifies to 10 over 3, right? 1,000 divided by 300 simplifies to 10/3, right? Actually, maybe I'll write it out. Okay. So we have 1,000 divided by 300 is equal to E raised to the natural log of 2 over 9 times T power. Now the variable we're solving for is in an exponent, right? If you have to solve for a variable that's in an exponent, what are you going to need? Begins with an L, an O, a G, an A. Logarithm, right? It takes a logarithm to solve for a variable that's in an exponent. So we got to get rid of the E. What gets rid of the E? Natural log, right? Remember, the natural log of e to the x is just x, right? You got to remember these properties, okay? So I can take the natural log of both sides, and 1,000 over 300 simplifies to 10/3. So I have the natural log of 10/3 on the left is equal to the natural log of e raised to the natural log of 2 over 9 to the T power on the right. I dropped the parentheses now. I didn't want to avoid nested parentheses. Right, it's the form over there. So we have the natural log of 10/3. You can leave the parentheses on the left or not. Okay. And on the right, our x is now natural log of 2 over 9 times t. So that on the right is just equal to the natural log of 2 over 9 times t. Now it's easy to isolate the t, right? You can multiply both sides by 9, divide both sides by the natural log of 2, right? Or multiply both sides by 9 over the natural log of 2. Okay. And so when we do that, okay, so we have 9 times the natural log of 2 on the left times the natural log of 10/3 is equal to 9 over the natural log of 2 times the natural log of 2 over 9 times t. Right? So you can see I just multiplied both sides by 9 over the natural log of 2. Okay. So the 9's cancel over here, and the natural log of 2's cancel, and I'm just left with t on the left, right-hand side. And now when I switch the two sides, I have t is equal to 9 times the natural log of 10/3 over the natural log of 2. And what are the units? The units are years. The algebra is not so nice, right? It's not the nice algebra you're used to when solving linear equations, right? But there are no calculators. So if you were allowed to use a calculator, you find the decimal, right, answer to this. You write out the answer to the 1 or 2 decimal places. But this is the exact answer. Okay. Are there any questions on that, ladies and gentlemen? Nada? Okay. So let's move on. I'm going to leave that rectangle up there. While we look at the next one. So on page 2, we're told a bacteria population grows exponentially. The initial population is 200 bacteria. The initial population is 200 bacteria. So that's A sub 0, right? That's the initial population. Okay. After 7 hours, the population has increased to 300 bacteria. So that tells us in our model over here, at t equals 7, we have A of 7, the amount of bacteria after 7 hours, okay, is equal to 300 bacteria. That's what this statement here says. After 7 hours, the population has increased to 300 bacteria. Right? We started off at 200 at t equals 0. Right? Remember, the initial quantity is at t equals 0. And then 7 hours later, we're up to 300 bacteria. Okay? So A of 7 is equal to 300. Find an exponential model for the amount of bacteria after t hours. Okay. So this is our model, right? A of t is equal to A sub 0 times e to the kt power. We know what A sub 0, the initial quantity is, right? It's 200. So we have A of t is equal to A sub 0, which is 200, times e to the kt power. Remember, kt is an exponent on the number e. It's not at the same level as e. Okay. Now, we're told at t equals 7, we have 300 bacteria. Right? So A of 7 is equal to 200 times E raised to the K times 7 power, right? All I did was reevaluate this function at t equals 7. So A of 7 is equal to 200 times E to the K times 7 power. Well, the amount of bacteria at t equals 7 is 300. So we replace A of 7 with 300. So we have 300 is equal to 200 times E. Instead of K times 7, we can write that as 7 times K, right? And now if I divide both sides, right, this is a product, so I can divide both sides by 200. And I have 300 divided by 200 is equal to E raised to the 7K power. We're solving for K, right? Trying to find the growth rate. So we're solving the stage, right? We're solving for the growth rate K. We know what A sub 0 is. We need to know what the growth rate is. Again, E to the set K is in the exponent, so we need a logarithm to solve for K, right? So we use the identity over here. Natural log of E to the X, it's just X. So we take the natural log of both sides. And we have the natural log of 3/2. Right? Zeros cancel. We have the natural log of 3/2 is equal to the natural log of E to the 7K power. So X in this case is just 7K, right? So we have the natural log of 3/2 is equal to 7 times K. And now you divide both sides or multiply both sides by 1/7. And now you have your K. Okay. Alright. So if I multiply both sides by 1/7, and 1/7 times the natural log of 3/2 is equal to 1/7 times 7K. Now when I switch the two sides, right, 1/7 times 7K is just K. Now when I switch the two sides, I have K is equal to 1/7 times the natural log 3/2. So now I can put my value of K into my model here, right? Now I have my exponential model for this problem.
I guess I'm wondering, why couldn't you just find like capital T from like the initial population was 200 and then after 7 hours it increased by 100. Why couldn't you just make capital T 14?
Because it's growing exponentially, not linear. You're assuming linear growth.
Okay, but it's not that.
It's shooting up rapidly.
Okay.
Yeah. That's why we got to do that.
Okay.
Okay. All right. So in our function here, we now replace K with 1/7 times the natural log of 3/2, and we have our exponential model for this problem. So A of T is equal to 200, right? The initial quantity is 200 times E to the KT power. Well, K is 1/7 times the natural log of 3/2, and then that gets multiplied by t. Again, all this is an exponent on the number e. This is e raised to the 1/7 times the natural log of 3/2 times t power. So if you want, you put all that in parentheses, right? Indicate all that is an exponent of the number e. Yes, ma'am.
Can you write k as the natural log of 3/2 over 7?
Yeah.
Okay.
Yeah, this is equal to the natural log of 3/2 over 7. Yeah. You can do the same. Yeah, you can do that. Certainly. So that's part A. Okay. How many hours will it take for the population to double? Well, you were saying 14, right? Is that what you said?
It is, yeah.
The time it takes for it to double is the natural log of 2 divided by k, right? From the rectangle. Well, what's k? It's all this, right? So this is equal to the natural log of 2 divided by, and I think I'm going to write it out Kennedy's way, natural log of 3/2 divided by 7. We have natural log 3/2 divided by 7. Okay. So we're dividing the natural log of 2 by this fraction, right? Keep, switch, flip. Remember that? Keep, switch, flip. So t is equal to the natural log of 2 over 1 times 7 over the natural log of 3/2. Keep, switch, flip, right? And when you simplify for capital T, you get 7 times the natural log of 2 over the natural log of 3/2. And that's in years. Oh, hours, excuse me. Units are hours. And that doesn't equal 14. Okay. Then it's all because, right, I drew the graph. It's shooting up. It's increasing rapidly. Okay. All right. Any questions on that, ladies and gentlemen? Okay. All right, so now if you flip over to page 3, we're going to talk about exponential decay. The exponential decay model is used to model the quantity of a substance that decreases with time. So let's just emphasize the difference in the two models. Okay. In the exponential growth model, okay, the substance or population grows with time. Okay. In the exponential decay model, okay, the quantity of substance decreases with time. So a lot of active substances, right? They decay exponentially. Okay. It is basically the exponential decay model is basically the same model as the exponential growth model, except for one important difference, right? So it has the same form. The model has the same form. The difference is the K. In exponential growth, K is positive. In exponential decay, K is negative, and it's called the decay constant or the decay rate instead of the growth rate, right? Or the growth constant. Instead of time for a substance to double, we have the time for a substance to decay in half. Okay? So the half-life of the substance is the time required for half of the substance present in a sample to decay. And so you notice the half-life looks similar, the formula for the half-life looks similar for the time to double, right? For the time to double, it's the natural log of 2 over K. For the half-life, it's minus the natural log of 2 over K. And then if you solve this equation for K, you get the decay rate is equal to minus log 2 over the time it takes for the substance to decay in half. So let's apply this exponential decay model to a drug. The drug lorazepam, used to relieve anxiety and nervousness, has a half-life of 14 hours. Half-life of 14 hours. So it takes 14 hours for half of the substance to decay. So we know capital T is equal to 14 hours. How much of a 2.5 milligram tablet is in a patient's body 2 hours after the dosage is taken? So we know the initial quantity of the drug is 2.5 milligrams, right? That's the size of the tablet. So the growth, or the decay rate K is equal to minus the natural log of 2 over capital T, and T is 14. So the decay rate is equal to minus the natural log of 2 over 14. So plugging into our model for A sub 0 and K, we have the amount of the substance at time T is equal to the initial amount, 2.5 times E raised to the KT power, and K is minus the natural log of 2 over 14, and that's multiplied by T. So this is the exponent on the number E, minus log 2 over 14 times T. How much of the 2.5 milligram tablet is present in a patient's body 2 hours after the dosage is taken? But now we evaluate A of T at T equals 2. And that gives us the amount of the drug in the patient's body 2 hours after they take that 2.5 milligram tablet. So A of 2 is equal to 2.5 times E. And now we put 2 in for T up here. We have minus log 2 over 14 times 2. And 2 and 14 are both divisible by 2, right? So 2 divided by 2 is 1. 14 divided by 2 is 7. And so we're left with minus log 2 over 7 as the exponent on the number E. And the units is milligrams. So the amount of the 2.5 milligram tablet after 2 hours in the body of the patient is 2.5 times E raised to the minus log 2 over 7 on the number E. That's the exact answer. If you're allowed to use calculators, you'll be able to write out a decimal answer. Riddle me this. The amount in the bloodstream after 2 hours, is it more than 2.5 or less than 2.5? Yeah, better be less. It's decaying, right? Right? It's declining. So, somewhere between 0 and 2.5 is the value of this Alright. So, there will be practice problems for the final exam, okay? But it won't be on Wednesday's test. Okay? So, have a good day, and I will see you